Let's get started, guys. Hope you had a good Wednesday and good Thursday. I want to talk to you guys about MAP estimators, maximum a posteriori estimators. And the example that I'm going to draw for you is from a kind of a task where we can compare maximum likelihood estimator with a maximum a posteriori estimator. And in doing that, maybe you can get the door if you don't mind. In doing that, the basic idea that I want to show you is that when you have a Bayesian estimator, a MAP estimator, what you basically are doing is assuming that you've seen some prior examples that look like your prior. Meaning that, you know, if, for example, we're going to be tossing a coin, and if our prior is that, you know, we think it's a fair coin, then in effect, what the prior is doing is saying that on this first trial where you toss the coin, in effect, you've already tossed it, you know, 20 more times before, and in those 20 times, you've observed, you know, 10 times that it was a head. So what the MAP estimator is doing is adding data, in effect, to your data. Your likelihood is from the data that you actually observed. Your prior is kind of like fake data. It's the data that you never actually observed, but it's based on your prior. You believe that that data would have existed. So it colors your estimation based on that prior. Does that make sense? So in many ways, Bayesian estimation, the prior is our belief, and our belief is coming from data that we never actually collected. We are using that to color the current data. So, and you know, that's what a bias is. Bias is a history effect that's influencing your decision making. So we're going to have a random variable x that is going to take on binary variables, and we have some prior probability of it being 1 as a probability q, and so the probability of it being 0 is 1 minus q. And so if we are throwing this dice, or this coin, let's say, so coin can be 1 or 0, and we count the number of times that it turns to be 1, so n is the number of times we got x to be equal to 1 in capital N observations that we made, then you know that n is just the sum of I is equal to 1 to n of the x's that we observed. And before one of our lectures, we found that, well, the expected value of n is just n times q, where q is the probability of it being equal to 1. So if you observed it capital N times the probability of it being x equaled 1 is the expected value of little n. And we also found that the variance of that was capital NQ 1 minus q. Okay, so we have some data set that we have observed. And our data set looks like this. So in this we have n number of times when x was equal to 1. And what we want to know is that we want to estimate the likelihood that the next observation will be x is equal to 1. And the point of our lecture today is to show that if we've observed this data, maximum likelihood is going to make an estimate based on only this data. Whereas map estimator is effectively adding to this data some other fake data, and that fake data is representing our prior. So that's our goal today. Okay, so given that that's our data, we have some likelihood that we're going to define, which is the probability of observing the data that we did, given that it was generated by a probability distribution that had this parameter Q in it. And so, you know, this joint probability is the individual probabilities and so that's equal to Q n times 1 minus Q capital N minus n times. So the log of the likelihood is equal to n times log of Q plus n minus n log of 1 minus Q. So in maximum likelihood, we want to find the parameter Q that maximizes our likelihood. So we find the derivative of the log likelihood with respect to Q. And so the derivative of the first term here is n times 1 over Q. Derivative of the second term is capital N minus n times 1 over 1 minus Q. We want to maximize this, so we set that equal to 0. That derivative is going to be maximized when QML, my estimate of that probability, is n over n, which is telling me that the maximum likelihood estimate of my parameter Q here is the number of times that I got x is equal to 1 divided by total number of times, which is the mean estimate for my parameter Q. Fine. Okay, so here's the problem. So the problem is that after one trial, if we get x of 1 is equal to 0, then n is equal to 0. So we didn't get any 1s on our first trial. So if that's the case, then my maximum likelihood estimate is 0 over 1, which is 0. So that's the problem. You made one observation, and that observation told you that you didn't get x is equal to 1. You got x is equal to 0. So your maximum likelihood estimate of the probability of getting 1 is 0. Here it is. That doesn't seem a very good estimate. So you really are influenced by the data that you see, even though you might have a belief that there's something else that's actually the truth. That's your maximum likelihood estimate. So that's the problem that we want to solve. So if we had a prior, then hopefully we could fix this. All right. So that's what I want to talk about today. If we had a prior, we could do better. So let's imagine a prior that looks like this. So let's begin with a discrete prior. P of Q, say it's going to take two variables. So maybe it's equal to m if Q is 0.5. So I'm writing the distribution now of this probability, this parameter Q. Suppose that we believe that this coin is fair and we have some probability m associated with it. And then we have some belief that it's not quite fair. Maybe the Q is 0.4, so it's more likely for it to give a 0 than it is a 1. and that probability is 1 minus m. Then I have 0 for otherwise. So now suppose what I want to do is write the posterior probability, the probability that Q is 0.5 given my data. So what's the probability that this coin that I'm throwing is fair? Well, that's the probability of the data given that it is indeed a fair coin times the prior probability that it's a fair coin divided by probability of the data, which is what? Is probability of the data given this condition plus the probability of the data given the other condition this is little p here. And that's it, because the third condition, its prior is 0. So this is, on the denominator is the marginal, the probability of the data. I integrated out the value of Q. So let's go ahead and write down what these things are. So this term here, probability of data, given that Q is 0.5 is my likelihood, that's Q to the power of n, 1 minus Q to the power of n minus n, capital N minus little n. So this can be written as Q raised to the power of little n times 1 minus Q, which is 0.5, raised to the power of n minus n, times probability, the prior probability, which is m, divided by the same term plus this term here, the likelihood. So after n is equal to 1, coin toss with n is equal to 0, then the probability of it being a fair coin, given my data, is 0.5 m divided by 0.5 m plus 0.6, 1 minus m, which is, that's the probability of it being a fair coin. The probability of it being an unfair coin, given the data, is 0.6, 1 minus m, 0.5 m plus 0.6, 1 minus m. So after one observation, we have some slight belief. So if m is 0.5, if my prior probability is that this is going to be, just as likely for it to be a fair coin as an unfair coin, after one toss, what I have is that the probability of it being an unfair coin, given the data, is slightly bigger than the probability of it being a fair coin, but not 0. So probability of it being a fair coin is definitely not 0. It's just that I have leaned a little bit toward calling it an unfair coin. So what this is doing is that basically it is adding data to our one trial. It's adding the prior. And so in principle, when we have something that we want to estimate, parameter that we want to estimate, and the way for us to estimate it in a Bayesian sense is to find that parameter that maximizes the probability of that parameter given the data, which is going to be equal to the parameter that maximizes probability of the data given the parameter, the likelihood, times the prior. So I didn't put the marginal on it because that's just a normalizing constant. So this division here that we're making based on this denominator, the denominator is just normalizing things. So if I find the parameter that maximizes the multiplication of my likelihood to the prior, that's my maximum a posteriori. And so when we find the log of this, argmax theta, okay, that's horrible. All right, let's go back. So when we want to find the log of this is the log of P of the likelihood plus the log of my prior. Now let's compare that to maximum likelihood. So when I want to find the maximum likelihood estimate, okay, now compare these two equations. See, in the Bayesian estimator, it's the same log here, but you've added to it this new data. Whereas in maximum likelihood estimator, you just have the likelihood. Does that make sense? This is what the prior is doing. And so if you have no prior belief, if P of theta is constant, if this is the case, then of course map estimator is the same as a maximum likelihood estimator. If your prior belief is not dependent on the parameter that you're trying to estimate, like in this case, then these two are the same. If, on the other hand, you have some prior belief that says it depends on, this probability actually depends on theta, the parameter that you're trying to estimate, then you're going to color your estimation. So the basic idea being ML is the same as map if the prior probability is not dependent on the parameter theta. Okay, so let's now go back to our coin toss problem and formulate a little bit more sophisticated prior probability, a continuous one. So in our coin toss problem, we had the probability of the data given the parameter that we were interested in, Q, and we wrote that, well, that made it so that our data would be distributed as follows: Q of n, 1 minus Q, n minus n. So that's the likelihood function. So let's now imagine our prior to be continuous. That means that the probability of Q. So probability of Q is going to be continuous. I'm going to write it like this: 1 over C, Q over Q of n, 1 minus Q, n minus n. This is called a beta distribution. Where any distribution has this normalizing constant in front of it. So So 1 over c would be the integral of this. That's the normalizing constant. So what does this mean? So if you were to plot probability of Q, so Q goes from 0 to 1, and I want to show you what does this mean, this function that I just drew here. So P of Q, this is what Q is the probability of when you toss a coin, you're going to get a 1. So if you toss the coin twice and you get it to be a head once. So n, little n is 1, capital N is 2. 1 out of 2 times you get this, you get a head. So we're going to put this in this equation here, and we're going to plot this as a function of q. It would look like this. On the other hand, if you toss the coin 4 times and twice you got it to be a head, it's going to look like this. So I'm just drawing P of Q here. I'm drawing this function when I have little n is equal to 2, big N is equal to 4. So I'm just drawing the shape of this prior. If on the other hand, if I have this other representation where I've thrown the dice or the coin, say 8 times, and 4 of them I've gotten a head, then I have this probability distribution. So you can see that it becomes more peaked the more you've experienced things, and the more you've gotten data. So this is how we're going to describe our prior. Are you really confident about the nature of this coin, in which case you're up here, or are you pretty, vague about it, which you're down here? Does that make sense? Yeah.
Big N there would be 8, right?
Oh, thank you. Yeah, thank you. So we're going to express our confidence about this parameter that we're trying to estimate, q, using a beta distribution. So the q can go from 0 to 1. Therefore, this integral, of course, has to be 1 because we're talking about probability distribution. And the shape of this function that we're going to describe our prior is dependent on how strongly we believe, that coin that we're going to be looking at is going to be fair. And if we're not so strongly believe about it, it's going to look like this. If we really strongly believe it, it's going to look like this. All right. So now we're going to look at our posterior. What's the probability of q given my data? We're going to have the likelihood. Here's the likelihood. It's q of n, 1 minus q, n minus n, times the prior, which is 1 over c, q of n, 1 minus q, n minus n, divided by the joint, the marginal, which is the multiplication of this times this, integrated over all the data. So it's going to be from 0 to 1. Okay.
Does it start recording?
I did. It's recorded.
I don't think so. Oh, yeah.
Yeah. Okay. So let's set our prior, and let's imagine what we would get. So we could have a prior that looks like this. We can also have a prior, of course, that looks like this. So we could have a prior that says, you have shaped like this, which is n is equal to 1, capital N is equal to 2. On the other hand, if you throw that coin many times and you keep getting tails, x is equal to 0, then you're going to get a prior that looks like this. N is equal to 1, capital N is equal to 8. This is q. This is P of q. Okay, so that's our prior. So let's pick a specific prior. So let's say that my prior P of q is 1 over c q to the alpha. Let's pick a particular one, 1 minus q n minus alpha. So I could pick a prior that looks like this, or I could pick a prior that looks like this. I could pick alpha to be something, and then say that's my prior. Now let's see what's the maximum a posteriori estimate comes up. So P of Q given data is going to be the likelihood, Q of n, 1 minus Q capital N minus n, times my prior, 1 over C Q alpha, 1 minus Q capital N minus alpha, divided by some constant. That's going to be equal to 1 over some constant d times q, let's multiply this out, n plus alpha, 1 minus q, 2n minus n minus alpha. Okay, so now what we want to do is find a q that maximizes the posterior. So let's see what that's going to do for us. So we find the log of this first. We get log of the P of Q given D. That's equal to 1 over D times this, sorry. I want to find the log of. So I'm going to get log of 1 over D plus n plus alpha times log of Q plus 2n minus n minus alpha log of 1 minus Q. So now I want to find the derivative of this with respect to Q. The first term doesn't give me anything. The second one gives me n plus alpha over Q. The second term, 2n minus little n minus alpha over 1 minus Q. I set this equal to 0. So I get n plus alpha over Q is equal to, sorry, this is minus. Right, because 1 minus Q, log of 1 minus Q, its derivative is numerator divided by 1 minus Q times the derivative of 1 minus Q, which is a minus 1. So this is 2n minus n minus alpha, 1 minus Q. So I have 1 minus Q over Q is equal to 2n minus n minus alpha over n plus alpha. So I have 1 over Q is equal to 2n minus n minus alpha n plus alpha plus 1. So I get 1 over Q is equal to 2n minus n minus alpha plus n plus alpha over n plus alpha, which is equal to which is equal to 2n minus n, sorry, 2n over n plus alpha, which means Q is n plus alpha over 2n. So let's see, what did we just do? So this is my map estimator. Let's see what it means. It says your best estimate of Q is the number of times that you got x is equal to 1 plus alpha divided by 2n. Why? Because what it's saying is that add to your data alpha over n, capital N. So if it was our maximum likelihood estimator, it would be n over n, the number of times that we got the positive result over the total number of results. But what we did is that we had a prior that said we have gotten alpha number of positive results over n number of results. So what it's doing is that it's adding to this, to become a map estimator, it's adding to it fake data, alpha over n, which was our prior. Yeah.
Just curious, is it common to use a similar structure for your prior as your likelihood?
So in this case, because you want it to be bounded between 0 and 1, you want a distribution that does that. And so in this case, it's easiest to use the same representation. Yeah. But anything will do. You just need to be able to define a probability distribution that's bounded. So the basic idea is, I just want to go over it one more time, is that in our maximum likelihood estimate, we had the number of times that we got the positive results over the total number of times. This is our data. What we have with the map estimate is that we have the data, n over n, but we've also added to it our prior, which is alpha over n. It's as if in your pocket you have data as you come to the table. And then you collect this data and you add it to the data that you had, and that becomes your maximum likelihood estimate. Does that make sense? Okay, so let's do an example of our approach using a classification example now. And what I want to get to is the fact that when we want to do classification, we can use Bayes estimation and then get to this idea of logistic representation of the classifier. So we've been doing regression, which is fine. We're having this linear representation when we have an input-output. In Bayes estimation, we can see that in order for us to classify things, we'll end up with a representation of a posterior that is also going to be linear in the parameters that we're trying to estimate. So then eventually in the class, we'll get to logistic regression, and you'll see how to do basically learning of the Bayesian estimator on a trial-by-trial basis. So the example that I want to show you is a simple one. You have some data which represents the height of individuals, and your random variable that describes the height is the gender of that person. So you could have a male, which we're going to have it as a 0, and a female if the gender was female. And we have some prior probability in your distribution that females have some prior probability of Q. So here's what your typical data is going to look like. On the x-axis, you're going to have your measurement y, and so we're going to start with the likelihood. We want to draw the likelihood distributions. So, let's go from 150 centimeters to maybe 200 centimeters, and you're going to get a distribution that sort of looks like this and like this. So this is going to be P of y, given that x is equal to 1. And we're going to have P of y given that x is equal to 0. So males and females, males have a height of about 180 centimeters, say females 160 centimeters on average. And our objective is to say, I'm going to give you a height of an individual, and you tell me what's the probability of that person being male or female. Okay? So what we want to know is what's the probability of being female given that you have measured a height. So you have a likelihood that describes the data. You've collected some data among people. You know that what the probability of height given that data, that they were male or female. That was your likelihood. So these things are given to you. And now what you want to know is that what's the probability of the person being a particular gender given this measurement that you made. So this is a classification problem. So of course that's equal to the probability of y given that the person is female times the probability of the prior probability of being female divided by the marginal probability of y being coming from a female person times the probability of the prior plus the probability of the male times the prior probability. This is the marginal probability of the height. Okay. All right, so let's write down our distribution. Suppose that probability, the likelihoods are normally distributed with mean mu1 sigma squared and probability of y being 0 also normally distributed with mean mu0 and sigma squared. So I'm going to assume that the variance of these two distributions is the same. So if that's the case, then the probability of x is 1 given my data is going to be the following. It's going to be the prior probability, q, times the normal distribution, which is 1 over square root of 2 pi sigma squared times an exponential minus 1 over 2 sigma squared, my data minus mu1 squared divided by the marginal, which is going to have 1 over square root of 2 pi sigma squared on the outside. Then I'm going to have a q times the exponential minus 1 over 2 sigma squared, y minus mu1 squared, plus the prior times the probability of it being x is equal to 0, which is an exponential minus 1 over 2 sigma squared, y minus mu0 squared. Now all I want to do is to simplify this equation for you. I want to show you that this probability can be written as a function of the linear things that we're trying to go after. So this looks quite nonlinear, right? So this function looks really nonlinear. What do we have? We have the measurement of the data, y. This is what we've measured. And we have some parameters, which are q, these means, mu0, mu1, and we have the sigma squared. These are the things that are the parameters of our data, and we have this thing that we're trying to estimate, which is the posterior probability. And the idea is, I want to show you that despite the fact that this is nonlinear, we can reduce this equation so that it becomes linear in the things that we're trying to estimate, which are the parameters. And once we do that, then we have just another case of a regression problem. So even though we're trying to do, estimation with this function that looks nonlinear, we can simplify it and we can get a linear representation of the parameters that we're trying to go after, and that's called logistic regression. All right. So how do we reduce this equation? So I'm going to divide this equation by the numerator. So you notice that this part of this equation is the same as this part of it. So the probability of x is equal to 1 given y, I'm going to divide this equation by the numerator. So I'm going to get a 1 on top. And when I do this division, I'm going to get a 1 in the front, because this term is the same as this term. Then I'm going to get this term here divided by this term. So I'm going to get a 1 minus q divided by q. And this term goes away. This 1 over square root of 2 pi sigma squared goes away. Then I'm going to have divided by this. So I want to now bring this ratio inside this exponential, because this exponential divided by this exponential, I can handle it because it's just this exponential numerator minus the numerator of this exponential. But it has this term in the front of it. So I want to take this and bring it inside the exponential, and by doing that, what I'm going to do is to basically represent this as an exponential of a log. So this is equal to, let's see if I can do it in front of it here. Okay. So this is equal to 1 over 1 plus, suppose I write this as an exponential of a log of 1 minus q divided by q times that exponential of that divided by what's left. So if I do that, then I get the following. So the inside of this exponential has these terms, has this term here that let me fix this here. So that the inside this exponential has a term that doesn't depend on my data and has a term that does depend on my data. But you notice that it is linear in my data. So this is like a constant plus something that's multiplying my data. So the inside of the exponential appears to be linear in my data that I've seen, y. And so this probability of x is equal to 1 given my data is 1 over 1 plus an exponential. Inside this exponential, there's a constant term, and then there is this term that's multiplying my data. So I'm going to write it as some parameter theta transpose times some vector y, where this parameter theta is going to be log of 1 minus q divided by q minus 1 over 2 sigma squared mu 0 squared minus mu 1 squared, and the second term is 1 over sigma squared times mu 0 minus mu 1, and then this parameter, this data that I've seen, y is 1 and y. Yeah.
You have the y square in there as well.
This is mu 0.
go up a little bit? So y minus mu 0 square has y square in it?
Yeah, you see it cancels out.
Oh, yeah.
Right. So the point being that we can write the posterior probability as a nonlinear function that in it, there's a term here that's linear that we want to estimate. So if we want to maximize the posterior probability, we can find the parameter theta that does it. And what is theta? It's going to be some vector here that depends on the terms of my distributions and my likelihoods. But it is now, I've taken my problem here and I've been able to factor out the parameters that I'm after and the data that I have, and it's linear in it. So it looks very similar to what we used to have, which is W transpose times X. Here now I have this term. So I have a posterior probability that inside the exponential has a linear component. And so finding theta map is to maximize this probability. And that's what we're going to do. We're going to do maximum a posteriori estimation by logistic regression. So this is a logistic function, and this theta here is the parameter we want to estimate that would maximize the data, this posterior probability. So for example, if we were to look at what this would look like for what's the posterior probability would look like for our data, so what's the posterior probability of the person being female given the data, it would look something like this. So if this is height, y, going from say 150 to 200, it would look like a function that looks like this. This is the probability of x is equal to 1 given y. Okay. So we made a logistic function. This is a logistic function. I've plotted it here for you. That describes our posterior probability. All right, any questions? So the basic story of Bayesian integration is addition of data to your actually observed data. And that addition of the data is reflecting the strength of your prior. So in a coin toss problem, if your prior is very strong, what that means is that you have added a whole bunch of data to your single observation. And that's what we're doing with Bayesian estimation. And so frequentists, people who view statistics as the problem of making estimation based on actual data, don't like Bayesian estimation because Bayesian estimation requires you to come up with a prior. And so you can get your hypothesis to pass if, of course, you have a very strong prior. Frequentists are maximum likelihood estimators. They make no assumption about the prior. But you can be both. I mean, if you want to be a frequentist, it's fine. You can be a Bayesian by saying, well, I'm going to begin with no prior assumption, which means that your prior assumption is flat in the parameter space. Okay, any questions? Yeah.
Could you, at the end of the lecture, could you speak about what the midterm will cover?
Right. We're going to cover everything until today. So you can begin making your notes. So the midterm is Thursday, right? And we'll give you, Ehsan will send you examples from previous years so you can see what kind of questions we've been given. And the only thing that's different this year that we didn't have before was the work on Fourier analysis. So be prepared for that as well. But otherwise, begin by reviewing your notes, making your cheat sheet, making your one-page, covering of your past few lectures, the lectures this half semester. And we'll have the exam here. I think you'll have an hour and a half to do the exam. And by looking at the prior year exams, you should be in pretty good shape. And I hope all of you guys do well. Yeah.
So is that one page single-sided or one page double-sided?
You can make it double-sided. It's okay. Yeah. Yeah.
I'm just curious, is it beneficial to try to directly maximize the likelihood over the log likelihood? Or is there any reason why it would?
Well, the log is a increasing function, so you don't gain anything by doing one or the other. Maximizing one or the other is equivalent. It's just that mathematically, if you're looking for a closed form solution, you're going to get it most likely with the log, especially if you have exponentials in your distributions. That's the only
I'm
reason.
just curious why in this case we didn't directly just go after the log likelihood.
Yeah, that would be fine. Yeah, right. Rather than doing it the way I did. I don't know if we can get to a linear representation. I haven't tried it. Does that give you the same thing? Can I linearize it like this?
I'm not sure.
Yeah, I don't think so, because the log of this is nothing easy. Yeah. Good question. All right, guys. See you Tuesday. Have a good weekend.
I guess it doesn't.